Hello, this is Mr. Stansbury. I'm going to take you through the notes on transformations of absolute value and quadratic functions. At the end of this, you should be able to say, I can use parameters to identify changes in characteristics of a function, and I can describe the effect of a graph on a graph given a transformation rule. Okay, so let's get straight into absolute value and quadratic functions. This is our absolute value function. This is our quadratic function. We're just going to compare and contrast these things, see what's going on. So here's the parent functions of each. Compare the domain and the range of f of x, which is the absolute value, g of x, which is the quadratic. Okay, so domain is what the x's can be. The x's can be everything. So domains are both the same, and we do all real numbers. It's basically the all real number sign looks like that. Or we could also write it as we go from negative infinity to positive infinity. That's another way to write it. Okay. The ranges both start at 0 and go up forever and ever. Start at 0, go up forever and ever. So the ranges are both the same as well. And we can write that just like we did this one here. We start at 0 and we go up to, and actually we include 0. So really we should make that a square, 0 and up to infinity, and you can never include infinity because it just keeps going. So there's the ranges for both. End behavior. So as well, let's write our little as statements there. Remember that as x goes to negative infinity, f of x goes to what? As x goes to positive infinity, f of x goes to what? So you'll notice on both of these, as x goes to negative infinity, this is going to infinity here, and this is also going to infinity. Okay. And then for as x goes to positive infinity, this is going towards, the y is going towards infinity, and the y is also going towards infinity on this one. So they are also both the same on that one. Okay. Describe the symmetry of f of x and g of x. They both are symmetric about the y-axis, right? You can reflect any one of these points straight across here, just like you could here. These will reflect straight across. That straight reflection right over that, right over the y-axis. So we would just say both are symmetric about the y-axis. Okay. Y-axis. Okay. All right. Now, let's see. Let's see the symmetry. Well, we also know that the vertex for both of these, it didn't really ask, but we can put it on there anyway. The vertex for both is 0, 0, right? What are the reference points of f of x and g of x? So for f of x, and this is the absolute value one, g of x. For f of x, we've got, let's see, we got 0, 0, 1, 1, and 2, 2, right? So we got 0, 0, 1, 1, 2, 2, right? For g of x, we've got 0, 0, 1, 1, and 2, 4. So we got 0, 0, 1, 1, and 2, 4. So it's a little different here because this is obviously going up. It's the rate of change is changing at all the time on this because it's a curved line, right? Compare the rate of change on the interval 1 to 2 for each function. Why are they different? Okay, we kind of just talked about that, but let's see the rate of change between 1 and 2. We go up 1 over 1, and this is for f of x is up 1 over 1, which gives us a rate of change of 1. And then for g of x, we go up 1, 2, 3 over 1. So we go up 3 over 1, which is a rate of change of 3. Okay. Why are they different? Yeah, because this one, the quadratic is curved. We're squaring each one of these numbers. That's why it's going up faster and faster each time, right? Okay. Okay, we're going to take a look at some examples, but first, let's take a quick little comedy break.
We thought he was sleeping, and all of a sudden I heard through the monitor, "Daddy, I have a joke for your career." I got like goosebumps, man. I'm like, wow. So I got to go up there, man. I ran upstairs. This is true. And I sit on the bed. I'm like, man, wow, you got a joke for my act, buddy? And he goes, yeah, I just thought of it. And I was like, whoa. I wanted to cry. I was like so touched, you know. I was like, really? Wow. What's the joke, buddy? And he goes, how come dinosaurs don't talk? I don't know. How come dinosaurs don't talk? Because they're all dead.
All right. So example 1, describe how to transform the graph of the absolute value function f of x equals absolute value of x to obtain the graph of g of x equals -2 times f of 1/4 x plus 1 all minus 3. Okay, so first thing let's do is let's figure out what a, b, h, and k are. So here's our little formula thing here, right? So the a is going to be whatever's in front of the function. So that's our -2, right? And then b is going to be whatever is right after the f of, so that's 1/4. H is the opposite of whatever this is here, or what do you put in for this so that you get 0. Either way you look at that, that is -1. And then the k is what's at the very end, which is -3. So there's a, b, h, and k. So we want to figure out what is the effect on the graph of the parent function of each of these numbers here, okay? Okay, so if you remember, a is affecting the y, right? So we're going to multiply all the y's by a, which is -2, okay? So what that means that these stretch vertically by a factor of 2, right, for the 2. And then the negative means that it reflects over the x-axis as well, and reflects over x-axis because of the negative. -3 is the k, the thing at the very end here. That just means that the whole graph, so we're going to look at the a and the k because that's dealing with just the y for starters. So that means the whole graph shifts down 3. Down 3. All of the points shift down 3. Okay, now we get to the weird one, which is the x part. So we're going to take x and divide it by b, which is 1/4. So it's really x over divided by 1/4, which is the same thing as x times, flip it over and multiply, 4/1. So that means it gets really x is being multiplied by 4. So that is going to be, instead of stretching vertically, it's going to stretch horizontally. Stretch horizontally by a factor of 4. Okay, and then the -1 here, because this is -1 plus 1 gives us 0. That -1 means that we are going to translate 1 unit to the left. Okay, horizontal translation, right? Shifts, let's do shifts. Left 1. Okay? Okay, so A says which parameters impact the x-coordinate? X-coordinate, those are going to, coordinate is going to be impacted by the B and the H. And then the y-coordinate is going to be impacted by the A and the K, right? Create a mapping rule to transform the points on F to G. So basically plug in our A, B, H, and K into this formula here and see what we get. So I'm even going to translate because here's our apply our mapping rule. I guess we can write it over here, right? So we officially have x divided by b, which is x divided by 1/4, which we figured out is actually x times 4. So let's do this, 4 times x. And then we're going to add the h plus -1, or you could just put -1. There's our x. Subtract 1. A is -2, so we take -2 times the y, and then we add the k, which in this case is -3. So really, this is the this is our formula. Let's clean it up a little bit here to say 4x minus 1 and negative 2y minus 3. Okay? Now we're going to take this, apply our mapping rule to the reference points here. So what we're going to do is we're just going to throw on a quick absolute value of x graph here and then translate our points. So let's do we'll do our f of x equals absolute value of x in pink here. So if we have our points here, 0, absolute value of 0 is 0, 1 is 1, absolute value of 1 is 1, absolute value of 2 is 2, so forth and so on. Absolute value of negative 1 is 1, absolute value of negative 2 is 2, so forth and so on. So we're going to get this big V shape for our absolute value graph. Okay, looks like that. Now we'll just graph some new points on here and see what happens, right? So point on the graph. So let's say 0, 0, 1, 1, 2, 2, and just see what happens with these, okay? So if we plug in our 0 for x and our 0 for y, we get 4 times 0. Oh, this one here, minus 1. So 4 times 0 is 0. Let's see. Let's just do this. We'll simplify in a minute here. So negative 2 times y, which is 0, minus 3. So that equals 4 times 0 is 0, minus 1 is negative 1. Oh, oops. I don't even have to write it there. We've got our symmetric point over here. Oh, wait, no. 4 times 0 is 0, minus 1 is negative 1, and then negative 2 times 0 is 0, minus 3 is negative 3. So 0, 0 is now at negative 1, negative 3. There's our new vertex. Okay, now, all right, we'll do the same for 1 and 1. So we'll do 4 times 1 minus 1, negative 2 times 1 minus 3. 4 times 1 is 4, minus 1 is 3, and negative 2 times 1 is negative 2, and negative 3 is negative 5. So now we're at negative 1, 2, 3, and negative 5 right here. Okay, and then we shall go to 2 and 2. So 4 times 2 minus 1, negative 2 times 2 minus 3 here. 4 times 2 is 8, minus 1 is 7. And then negative 2 times 2 is negative 4, and negative 3 is negative 7. So we're at 7. Oh, oops, I did this point here backwards. Hold on just a second. Let's fix that. Oh, instead of over here, we got here 3, negative 5, and then we got 7 and negative 7, which is right there. Okay, so we know that, oops, I got a little straight line drawer thing here. That should work. There we go. So we get, that's one part of it. And then they're asking for the symmetric point here. So since the vertex is negative 1, negative 3, our symmetric point there is negative 1, negative 3, right? So that's going to be the same point here. So basically they're saying if we take this here and we make ourselves a little mirror image right here, what's the symmetric point to this going to be? That's negative 1, negative 3. What is the symmetric point to this going to be? This is over 1, 2, 3, 4 here. So it's going to be 1, 2, 3, 4 more. So that's at negative 5, negative 5. Instead of having to go through and doing the math again, we could just do our little line of symmetry there. And then this is over, let's see, that's 7, 8. So then it's going to be 8 more from negative 1. So that's going to be negative 9 right there. And then we can draw our line there as well. And that's what our parent function looks like.